In today's lesson, we're going to be learning about Descartes' rule of signs and complex conjugates, and in the next video, we're going to be also talking about the rational zero theorem. Descartes' rule of signs is basically a rule that allows you to identify the number of positive and negative and imaginary zeros. And this can be really helpful when you're trying to graph a polynomial or solve a polynomial in order to determine how many positive answers you're going to get, how many negative answers you're going to get, or how many imaginary answers you're going to get. So it's not how to actually solve, it's just to tell you the number of each kind that you're going to have. So there's two parts to this rule. The first part is dealing with the positive real zeros, and what this says is that the number of real zeros that you will have is the same as the number of changes in signs of an equation less by an even number. And I will explain what that means here in a minute, but you want to go ahead and write that down. The same rule applies for the negative numbers, so the number of negative real zeros is the number of changes in signs, but instead of using the original equation, we're going to use f of negative x, and I'll show you how to use that. And it's always that number or less by an even number. And what that means is basically if you calculate there's going to be 3 negative real zeros, subtract 2 from that, that means there could also be 1 negative real zero. And again, we'll go through an example so you can see what that looks like. In example 1, it says state the number of possible positive, negative, and imaginary zeros, and then make a chart using this information. So I've got the equation here, f of x equals 2x to the 5th plus x to the 4th plus 3x cubed minus 4x squared minus x plus 9. Obviously, this is not an easy one to factor, and we don't know how many zeros we're going to have that are positive, negative, or imaginary, and this is where Descartes' rule is very helpful. So what we're going to first start off by doing is identifying how many total zeros we can have. And if you remember from previous sections, the exponent, the degree, is going to tell you how many zeros you're going to have. So my degree here is 5 because it's the highest exponent, so I'm going to have a total of 5 zeros. Okay. Then we need to start determining how many positive zeros we could have. So what this says is we're going to use the f of x equation, and we're just going to count the number of sign changes. So the way I do this, I'm going to go ahead and rewrite this equation here, is I just write out my equation, keep it exactly the same and in the correct order, so you always want to make sure it's in standard form. And then I just use my pencil and I go through and I put little loops where it changes from positive to negative or negative to positive. So here we've got plus, 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 so none of those change. But then we go from positive 3 to negative 4, so there's a sign change. Okay. Then we go from negative to negative, does not change. Negative to positive changes. So this had 2 sign changes. So what that means is that you could have 2 positive zeros, or if you always subtract 2 from that until you get negative numbers. So 2 minus 2 is 0, so I could have 2 zeros or 0 positive zeros. Okay, so you always take the number you get minus 2 and you keep subtracting 2 until you hit negative numbers. Okay, so I could have 2 positive answers or no positive answers. Then to do the negative possible zeros, what we're going to do is take the original equation and we're going to use f of negative x. And remember, if you have something different in the parentheses, that means you're going to plug in that number into the original equation. So instead of just plugging in a regular x, I'm going to change all my x's to be negatives. And that's going to look like this. F of negative x will equal 2 times negative x to the 5th plus negative x to the 4th plus 3 times negative x to the 3rd minus 4 times negative x squared minus a negative x and then plus 9. And then from here all you have to do is simplify. So basically any odd power will change signs, any even power is going to stay the same. So because the negative x to the 5th is an odd power, this 2 will become negative and it look like negative 2x to the 5th. This is an even power, so it's going to stay a positive. Negative x to the 3rd is an odd, so this is going to become negative 3x to the 3rd. Negative x squared is even, that means that's going to stay a negative 4x squared. And then 2 negatives here make a positive, so it'll be plus x, and then obviously the plus 9 does not change. So now when we look for our sign changes, we're going to be looking for, again, from positives to negatives. That means we have one change here, we have another change here, we have a third change here. What this says is that we could have 3 negative zeros, or we always subtract 2. 3 minus 2 is 1. So we could have 3 negative zeros, or we could have 1 negative 0. So right now we have 4 different options: 2 positives or 0 positives, 3 negatives or 1 negative. And the easiest way to combine all this information is to make a table. When we make our table, we're going to have 4 columns. The first column is going to be the number of positive zeros. The second one will be the negative one, and then the third one will be imaginary solutions. And the last column is always the total number of zeros. And so when we fill into each column, the first 3 columns have to total up to 5. And we say 5 because that was our highest degree. So every number here will have to add up to 5. Now, how we fill in is using what we established in the second and third steps here. So we have 2 positive zeros or 0 positive zeros. So I'm going to go ahead and do every combination of positives and negatives that I can, and then fill in the imaginary column accordingly. So I said I could have 2 positive zeros and 3 negative zeros. Because these already add up to 5, and that's the most I can have, that means I won't have any imaginary zeros if that's the possibility. I could also have 2 positive zeros and 1 negative. So that's a total of 3, which means I'd have 2 more zeros and they'd have to be imaginary. The next combination would be if I had no positive zeros and 3 negatives. That would leave us 2 imaginary numbers. And then lastly, 0 positives with 1 negative would leave us 4 imaginary numbers. And now this chart tells us how many of each type of solution that we could have. So if you are solving and you find that you have 2 positive answers, then you know you're either going to have 3 negatives or 1 negative with 2 imaginary numbers. So this eliminates the types of numbers that you need to solve for, which in large polynomials makes it a lot faster. Okay? And you might, if you know you don't find any positives, then you know they're all going to be negative and imaginary solutions. Okay, so this is just a chart to help you identify the kinds of solutions you should get, and as well it could help you with graphing or other similar things. Now if you'll notice that in this chart, when you look at the imaginary column here, there's kind of a unique property that happens. This column, if you notice, has all even numbers in it. And there's a special reason for that, and that's what leads us into our next theorem, which is the complex conjugate theorem. So basically what this says is that if you have an imaginary number that's a 0, then its conjugate or its opposite will also have to be a 0. And the rule is that complex numbers will always travel in pairs. That means that if I know 2 plus 3i is a solution to a polynomial, that means it also has to have the solution to minus 3i. And remember, conjugates just have the same numbers but opposite imaginary signs. Okay? So that's a really important rule, and this can be useful if we're writing a polynomial, and I've got an example of that written here. It says, write a polynomial function of least degree with zeros -1 and 5 minus I. So when it says least degree, that means you want to have the exponent, the degree, to be as low as possible. And to do that, you have to figure out how many zeros there are going to be in this problem. So we already know that -1 is a 0, and then we also know 5 minus I is a 0. And remember, because of this special theorem, that means that if 5 minus I is a 0, that also means that 5 plus I is also a 0. So here we have 3 different zeros, which means my degree will end up being 3. And to write the equation, what we're going to do is put these in factored form. The -1 we're going to go ahead and plug in. So this will be x minus -1. And then we're going to do the same thing here. We're going to have x minus 5 minus I, and then we're going to have x minus 5 plus I. And I always do subtraction to make sure that you're getting the signs correct, especially if they give you the answer on its own. Because remember, when we are solving, our sign changes. So a -1 will have to become a +1. So we'd get x plus 1. I'm going to distribute the negative here and get x minus 5 plus I. Same thing on this one, x minus 5 minus I. And then to actually get your answer, you just have to FOIL. I would always suggest foiling the ones with the imaginary numbers or square roots, doesn't really matter. I would always do those first because that way things reduce and cancel, then deal with the other numbers. So if I'm going to distribute here, I'm going to get x squared minus 5x minus xi. Then I'm going to keep distributing. So we get -5x positive 25, and then positive 5i. And then finally do my I to all three terms. So I get positive ix, negative 5i, and then negative I squared. So this is just me distributing through all of my terms. Then you can go ahead and simplify. Notice that my negative xi and positive xi cancel. Same with 5i and negative 5i. And then remember, I squared is the same as negative 1. So this is the same as writing negative 1. And now we can simplify that. So we have x squared, negative 5x and negative 5x is negative 10x. And then we have 25 plus 1, which is 26. And then we can bring down the x plus 1 from the original and FOIL this out. So again, foiling, we'll do the first term times all three. So we get x cubed minus 10x squared plus 26x. And then do the 1 to all of the terms. So x squared minus 10x plus 26. And lastly, combine like terms. So we have an x cubed, negative 10x squared plus x squared is a negative 9x squared. 26 minus 10x, those are going to get you a positive 16x. And then lastly, the plus 26 at the end. And there is our polynomial of least degree with zeros negative 1, 5 minus I, and 5 plus I. Okay? So always plug those into an equation using subtraction, simplify if you can, and then multiply it all out, and you're done.